So I thought I'd do a interesting video today, and by interesting I mean a video where I narrate over it, because I wanted to touch upon something that is kind of unique in the lineup of the RCs that I have designed and built, and that is what is Mudv1? Why is it called that? What's its origins? Why does it exist? And why does it break down all the time? So if you're not familiar with this channel and with the videos that I make, I have a lot of different videos and different subjects, a lot of which include engineering projects. And a favorite of mine is RC cars and RC trucks, primarily anything involving mud, snow, and sand and water, loose materials to drive on because those are the most challenging, or at least the challenges I like to build machines for. Uh, in off-roading, there is essentially two methodologies. You can go fast enough to use momentum to overcome the obstacle so that you sort of end up on the other side of it or end up at the top of it, and hope that you don't break in the process. You're pretty much counting, and that kinetic energy is exchanged for forward progress through an obstacle, at the cost of possibly damaging your machine at full scale, a real vehicle, or even a small toy RC. I am not particularly interested in that. I like RCs or real vehicles, such as the Cooting Quadractor I have, that can continue to maintain their pace through any terrain without having to exchange kinetic energy to keep going. So it's sort of like a duty cycle of off-roading. It's the ability to continue to have forward progress without needing to exchange that built up energy, i.e., you're not trading speed for forward progress. You're continuing to gain forward progress by having enough traction, enough flotation to just keep pushing through the terrain or over the. So while I do not possibly have the financial means to build an unlimited assortment of oddball off-road vehicles to pilot personally, it is much more viable to make remote control cars or scaled off-road vehicles because luckily terrain, mud, snow, and sand acts very, very similar at 1/10 scale or full scale. There are some differences, but they're not easier at 1/10 scale or full scale, so it is challenging for both. Upon learning this, coming to this realization that I could explore alternative means of locomotion in challenging terrain, such as sand, mud, snow, and water, at a smaller scale that I can afford to rapidly prototype different various off-road machines, I began brainstorming them. And a number of years ago, I came up with a machine called the Decanator. And at the time, I thought it would be the ultimate off-road machine at both full scale and small scale, or at least, again, with quotations on there, ultimate off-road vehicle in soft terrain such as sand, mud, and snow and water. And I keep mentioning those mediums because a off-road machine can tailor to many different terrains, such as high-speed desert racing, rock crawling, the list goes on, and that's kind of the beauty of off-road. There's no such thing as one proven meta. There isn't just a solution. We have been driving off-road, or at least pulling horse-drawn carts with wheels for hundreds of years, and to this day, we have yet to figure out the ideal machine that can traverse all surfaces, either pulled by a horse or self-propelled. There's no such thing as the perfect tire. There's no such thing as the perfect amount of tires. There's no such thing as the perfect anything yet. It's the reason why you can buy such a wide array of ATV and truck tires for off-roading. The tread style can vary massively because no one has yet really figured out the most perfect tread. And tread for tires is just one small portion of the off-road equation. There is much debate on to how much flotation you want, how much you want to sink, how much compaction you need in the materials, how much speed of the tires do you want spinning, do you want them to go slow, do you want them to go fast? And this is, of course, ignoring the mentality of just going fast enough that you can sort of plow over your terrain. Which leads me back to the notion of sustainability. And I mean the ability to sustain forward progress. After all, if just carrying enough speed and energy to enter a mud hole, a sand trap, or a large tundra of snow to get to the other side was always acceptable, you would see militaries, tractor companies, and all sort of other manner of off-roading ventures just packing as much horsepower and as much entry speed as possible to hit these terrains and get to the other side. But of course, that is completely unrealistic. All machines entering an obstacle with enough kinetic energy to get to the other side would destroy themselves eventually. So you're going to want something that can continue to push its way through terrain, over the terrain, without having to exchange that potential energy for forward progress. That's why things like mud skimmers or mega trucks that move so quickly over water that they hydroplane, while that is a neat concept, it's more of a trick. It's more like finding an obstacle that's exactly long enough that you have exactly enough energy to get to the other side, and that has few enough obstacles like boulders inside or hidden within the water that won't damage suspension components. It's simply not sustainable. So it has never really interested me beyond a neat trick or something that would make for a short YouTube video or demonstration of, wow, wasn't I lucky, I just barely made it, versus something that if you drove out into a swamp, you could continue to go for hours, if not days, with a sufficient amount of fuel and never get stuck because you are no longer exchanging that potential energy for forward progress, but actually maintain. Of course, such a machine would be, for all intents and purposes, the holy grail of mobility. There's a reason that when you see machines, they're designed to move at slow paces across or through difficult terrain continuously. They are very different in design because the engineers that poured all their efforts into them were trying to accomplish what is essentially the perpetual motion machine of off-road, a vehicle that never succumbs to being hung up and just keeps moving forward. An elusive goal, but one that in an RC at 1/10 scale, you can try many more combinations until you get something that works. Because at full scale, as you can see in some of these older machines from the 1960s, 70s, and 50s, in research and development for militaries of the world, these were very expensive endeavors to fund. And a lot of them, if not essentially almost all of them, failed at their intended goal for one reason or another. They may have had very high performance, but they may have had very low reliability, or the cost of manufacturing may have been very high, or they were so min-maxed at one specific terrain type, such as mud, that maybe they failed utterly in snow or sand. Lucky for me, living in the 2020s, we have access to 3D printers. And of course, materials scale in their structural integrity as they get smaller or larger, and it's based on the square root law, I think it's called. It's pretty much that when an object becomes twice as big, it becomes 8 times more massive or more heavy due to the volume to surface area ratio. This means that larger objects are weaker because they have more inertia and mass and potential energy that they have to survive colliding with objects or resonating or just existing in general under gravity. So smaller objects like an RC car, while it may perform very similar in off-road terrain, the materials it's made out of can be much weaker than you would use for a full-scale vehicle. And thus, I am allowed to get away with using just standard PLA plastic and 3D printing most of these designs, and they survive fine at 1/10 scale because they are magnitudes times stronger than they would be if they were 10 times bigger. As a quick aside, it is not theoretically impossible to replicate the same structures I have designed at 1/10 scale, full scale, and have them fail. They would just need to be made out of much more exotic materials, such as forged magnesiums and laminated carbon fibers. They would be quite expensive, but you could theoretically laminate up anything you've 3D printed from solid blocks of carbon fiber, and they would also survive, as their structural properties, the tensile strengths of most carbon fibers are hundreds of folds, well, not hundreds, but enough that they would be able to replicate the structural properties of much weaker PLA, but at full scale. But anyways, back to the topic of off-roading and the Mudv1, which is what this video is all about. Now, this long-winded exposition of context for what the heck Mudv1 is because you need to know why Deconator was designed and why it looks the way it does. Uh, there is very few, if no, similarities between Mudv1's drivetrain design and any real-world full-scale off-road machine. I was pretty much going into this blind and just hoping that my engineering prowess would allow me to come to a solution that would allow for the tires to be driven with so little hang-up, while also being able to be steered. And doing so affordably, having all the parts essentially 3D printed with as few over-the-counter parts as possible to reduce. Now, a huge principle in industrial design is rapid prototyping. And you want to fail fast. You want to learn what won't work as soon as possible so that you do not build up an entire skyscraper of innovative designs on a foundation that's fundamentally flawed. So when designing anything completely new and revolutionary, like Deconator's drivetrain and design, you can't simply build all of Deconator. You have to make sure its core components work. And in this case, it was going to be the gearboxes. These gearboxes have, well, there was many different variations of them. That was the thing. And I wasn't certain what was the best way to convey power from a motor down to the driveline. The motor, of course, had to be over the waterline if this was going to float from the tires. The tires, of course, giving the buoyancy for this to float over mud and water. So I had to transfer the rotational forces of the motor down into the axle. And at the time, I had not built anything like this before. And not only did this have to work, it had to be very reliable, very compact, and resistant to mud and water ingression because there was no realistic way I was going to seal the bottom of this drive box. The original design called for chain. It is known that chains, drives like chain on sprocket, can be subjected to mud and water and they do not prematurely wear out. They will wear out quicker, but they should survive the rigors of what I was going to put it through. There are plenty of ATVs out there and I have seen 6x6s with just their raw chain exposed to all the elements in mud and sand, and they seem to work fine as long as you keep them tight enough. Again, it will more rapidly wear out your sprockets and chain, but in my case, that didn't seem to be an issue as, like I said, smaller objects tend to wear out a little slower because they have better structural properties. And that's just a technology that I knew would work. It became evident very quickly that chain and sprocket would not be the correct use for this design. And that is mostly because at these scales, this tiny little chain and these tiny little sprockets are fickle both to 3D print the sprockets, their fitment and tight, adjusting the slack out of them would be very challenging. And at the moment, the design of the gearbox was still in its infancy, and there was no easy way to even install the chains within the confines of this small space. I fell away from chain drive, and I looked for an alternative. This would be found in the form of timing belts. So 3D printers, like hobby grade 3D printers, they have these small rubber timing belts. And you can get exceedingly strong ones with Kevlar laminations in them that would meet or exceed the strength of the very minuscule chain that I was going to run in the setup. So I didn't see any issues with these belts conveying the load, but it would mean that I have to learn how to 3D print pulleys. And I did. However, this design had many iterations, as keeping the belt from skipping on the 3D printed teeth of the timing belts, combined with a whole other avenue of issues, which I will not bore you ad nauseum by describing, just simply meant that timing belts weren't going to be the solution either. I realized that even if I could make the timing belts work, the biggest issue with them is they had the lowest survivability factor when ingressing mud and water. You simply don't expect rubber timing belts submerged in gritty water and grime to not pack the teeth of the pulley that they're wrapped around and thus slip. So I looked for an alternative. Now, You may have already considered gears. Why wouldn't I have thought of gears? Well, the answer was quite simply a limitation of understanding how to design gears in CAD. At the time, SolidWorks. I wasn't certain about gears. I simply lacked the education for how gears worked, and thus I shied away from them for systems that I understood. I understood how chain and sprockets and pulleys and timing belts worked as I had used them before in the past in previous jobs and designs, but I never designed gears from the ground up. I did not at the time understand pitch or the angles at which the teeth would intermesh with one another or anything. However, I thought it was time that I would finally learn because gears could very well have been the answer for these gearboxes. And fortunately, they were. There's absolutely no question. The gears that I eventually implemented in these gearboxes would be the right solution for the problem I had. And best yet, they offered superior grime and mud ingestion capabilities. You see, 3D printed gears work fantastic. They have very, very low coefficients of friction. And if they wear out, you can just print new ones very affordably and rapidly. And plastic gears, due to the way that they wear away or erode on one another, if they're ingesting material, they don't immediately fail. They'll just start sharpening or getting smaller until they fail, but you can check in on them from time to time to see how they're doing. And in all the testing with these gearboxes, they showed minimum to almost no wear, despite being subjected to huge quantities of grit, sand, water, mud constantly running through them. I didn't even bother putting lubrication on these gears because there would be no way the lubrication would ever last on them. And they were lubricated by the mud that they ingested, and yet they work perfectly fine. If you don't mind extra backlash in a design, you can space the gears quite far apart from each other, large enough that any materials that they ingest will fit between the teeth and just get spat right back out the other side. Now, you may be wondering how I would know this. I could guess or estimate or make theories about it, but it had to be tested in the real world. So I designed a testing rig. This first generation was called Quakernator, based on this RC body that I got on eBay that just says Quaker State for some reason. And it's essentially a Tamiya Blackfoot that the entire rear drivetrain has been removed and replaced by one of the five gearbox drivetrain setups that the Decanator would run. And I subjected this test mule to all sorts of abusive environments to really push it to the limits to see how the drivetrain would hold up. And it held up wonderfully. It didn't have any issues at all. I was very satisfied with the results. There was just one major problem, which was the test mule was quite limited in its off-road capabilities. It is rear wheel drive, and even with the dualies and no hang-up, and pretty adequate mud, sand, water, and snow capabilities, it couldn't be pushed into the deeper, more severe mud holes and under longer endurance runs that I had planned for Decanator. So without really pushing it to the limit, I couldn't be certain that this was going to work. So I needed a solution. The solution would come in the form of Mudv1. Gosh, I don't even want to check the timer on this, how long I've been narrating, and I've just barely started talking about Mudv1. So Mudv1 would be a test bed for the Decanator gearbox, but in an all-wheel drive system. So this would be four-wheel drive, which would mean that it would be much, much more capable of traversing the terrain and the environments that Decanator was intended to go. And thus, it could be run longer in worse conditions, and I could test out more of how the drivetrain would survive. But how do you test a drivetrain that you only have one example of in a machine that you need four-wheel drive? Simply put, you make it the transmission. And where the outputs for the tires for Decanator would now be drive shafts, or in this case, it would just be a really long Decanator axle that would migrate to both the front and rear axles off of a Red Cat Everest. Now, Mudv1 had another purpose. Now, when I design something, I want it to be as multifaceted as possible with its applications because, after all, I'm investing huge amounts of time and energy engineering these, printing out prototypes, testing them, refitting them. So I don't want anything to just sit around after proving one point. I want it to prove as many points as possible. While designing Decanator, it came to my attention that in the state that I reside, there is a competition called Ledge Stock, and there is a mega truck competition that's part of that. And as mega trucks, if anyone here is already aware, they are large off-roading trucks. They're like, the best way to describe them is they're monster trucks, but you remove the large flotation 66-inch tires and you replace them with narrow tractor tires. This allows them to be much faster because you don't have the rotational mass of these gigantic tires, and they tend to be better in the mud because narrow tractor tires cut and slice through the mud easier than large flotation tires. Now, circling back to that whole theory of potential energy being traded for progress, a monster truck is very much more likely to get through a more challenging mud hole than a mega truck because a monster truck can float through the mud hole while slowly making progress, but pushing a wake of mud out from in front of its tires. Whereas a mega truck may carry a huge amount of speed into a mud hole, pierce that mud hole quite deeply with its narrow tires, but eventually get hung up. That said, because most because most bounty holes is a term for long, muddy trenches that people who build mud trucks and mega trucks compete to see how far they get or how quickly they can do them. Because these trenches are only so long and only so deep, it's very plausible to carry enough energy in from the beginning to just maintain that energy just until the end to win. Whereas monster trucks may take too long to not get the highest or the best time and thus not be actually as competitive versus a mega truck. The other issue is these are people who need to transport these IRL full-scale machines to and from such competitions, and maneuvering humongous 1,200-pound monster truck tires, 4 of them, and installing them on your truck and then replacing them between events is very, very costly and difficult. But packing in a narrow, much lighter mega truck with tractor tires that you can just unload and load back onto a trailer is just way more feasible. So mega trucks tend to have narrow mud tires, tractor tires, where monster trucks tend to have large balloon-like low pressure tires, which are usually better for jumping onto because they have more cushion. But I digress. I'm getting way off point here. The point being that at this RC competition, there is a bounty hole-like mud trench, and it is very challenging from all the previous YouTube videos I'd seen. So you would build a mud truck to get from one side to the other. And I thought this is the perfect opportunity to implement Decanator's future drivetrain into a mud truck that would be compliant for this competition. Now, this mud truck would have many advantages as it would be built completely from scratch for the sole purpose of driving through the exact terrain that the course was composed from. So I wanted to make it a little bit more challenging on myself. I thought it would be funny if the truck was more of a sleeper, meaning that it would not appear that it would be very capable from the outside. It would lack all the normal telltale signs of a mega truck. It would not have very big tires, it wouldn't be jacked up, and it would look more like a street vehicle, at least from a distance. And even more funny would be if it was based on a Hummer, like an H2 Hummer, because those are notoriously bad off-road compared to all the alternatives you could possibly drive. So I thought that would make for a really fun engineering challenge. A sleeper mud truck that was rule compliant for this mega truck competition that would simultaneously be a test bed for Decanator's gearboxes while bringing a whole host of novel mudding technologies to the table to test. Now, since the rules, this is at the time, this is years and years ago, before some of the new rules were implemented. There used to be no 3D printed tire rules, which I'm pretty sure exist because of me, and there used to be no rim size restrictions. It was simply don't make the tires more than 3 inches wide, and they have to that's pretty much it. There wasn't really a lot of rules back then. If you wanted them to have chevrons or mimic a tractor tire, that's all that really mattered. So I set off to design 5-inch tall tires that were 3 inches wide because those were at the time legal. But the catch was there was going to be as little hang up between the tires as possible. In all of the historical mud, snow machines that I've seen, you don't want hang up. That's kind of the problem, right? If you have a vehicle that floats in the medium you're traversing, then the only way to be stopped is by getting high centered. You pretty much are going to get stuck on top of or push through so much material with static parts of your vehicle that you can't make progress anymore. Now, to give away a little secret here, I call it the golden ratio. If you can have 2 times more traction contact patch with the material you're trying to push through than static surface, you pretty much shouldn't ever get stuck. Now, in layman terms, that just means if your tires present a surface area that's twice as wide as your axle hang up and your belly hang up, you should never get stuck. A perfect example of this is Mudv2 or sometimes Mudv1, but we'll get to that later. And that they have just enough tire traction force versus hang-up force that they're seemingly unstoppable in mud. And this works at full scale too, but it's very difficult to attain these proportions. But that wouldn't be the only trick that Mudv1 would have up its sleeve. You see, because of the long wheelbase, there's a lot of hang up in the center. This vehicle is also to be amphibious, which means that at the time, the blue foam insulation, which was going to be how it was going to float, would need to be in contact with the water or mud to keep it from sinking. But that means you have a ton of hang up in the middle that is going to stop you from going forward. So my trick was to add an auger. It's essentially a screw drive. So if you're not already aware, the invention of the propeller way long ago was originally an Archimedes screw. Because an Archimedes screw can push fluid-like materials, including mud, and you put that underneath your vehicle, you suddenly have a propeller. But not quite. You see, an Archimedes screw is very inefficient for propelling a machine through water. A propeller, which is essentially a section of an Archimedes screw, but rotating much faster with a different pitch to its blades, simply works better. But in mud, an Archimedes screw should be much more efficient, as it can convey thicker, gooier materials more continuously without getting clogged. For example, there are these Russian and American off-road prototypes that use screw drive very efficiently. So I was going to combine screw drive with tire propulsion. Pretty much the tires would do the majority of the propulsion, but at the moment that the vehicle would start to high center, the screw would now be submerged in the medium and push itself forward. Now, in principle, that should work fantastic. I was ecstatic about testing this theory. Sadly, I don't know if this video will either contain or will not contain footage of the first tests of this inside my house. It's worth noting that the pitch for the Archimedes screw is exactly the rotational speed of the tires. I was very proud of figuring out the math behind that little principle. So that means that as the tires move forward, the path of the tread of the Archimedes screw moves at the exact same speed, so that it would not excavate too much material or slow down the vehicle moving forward. It would be like a caterpillar's tractor, a caterpillar's track on like an excavator would continue to move at the same speed of the tires, and thus everything would work in conjunction to just keep the vehicle moving. Now, engineering and bringing your ideas in your head to the real world is probably one of the most sobering experiences you can possibly achieve. It's almost transcendent because you can go from being 100% convinced that something will work perfectly to completely baffled at how wrong you could possibly have gotten it. Because there were so many shortcomings with this design that I could not have foreseen that only testing it would reveal. Now, this is, of course, why prototyping should always be an option before you move up to full scale. If I was working for a government contract or for a vehicle manufacturer and I told them that this idea would work, and then we invested all the time and effort and built a full-scale prototype to find that it didn't work, well, that would be a big waste of resources and it looked really bad on me. But since this is something that could be tested out within a month, 3D printed and run in a real-world simulate, I could rapidly figure out that this does not work as I had intended. The reason for this is because of the hang-up at the center of where the screw comes out. Now, I had designed the screw to taper so that material would be pushed up and around this low hanging point, which would have worked fine. The problem is, in almost any other off-road setting, such as just driving over a regular trail, if you hit any sort of rock or stick, you essentially have a pivot point at the very bottom of the vehicle that the vehicle would always tip over on. And it doesn't help that this vehicle is very narrow. And of course, you can't really make the vehicle wider because then there would have been less importance to removing the hang up in the narrow section in the middle. Because the vehicle would be wider, it could better compensate with wider tires to just simply push that material in the center. And remember, I am attempting to build a quote unquote sleeper mud truck. I do not want the tires to come outside of the wheel arches because then it would give away what's really happening underneath. So while this design, ironically, was never tested in the mud, it was run in the snow. I could pretty much guarantee right off the bat that it wasn't going to work in the mud because this vehicle would tip over if you looked at it the wrong way. It did propel itself in water. It's worth noting that the first version of Mudv1, the flotation was mounted higher than the tire tread, so the tires could not provide adequate propulsion in the water. So in the water, the screw did provide forward thrust, slow, but it was there. But what I did notice that was successful about this design was that the tires were very good in the snow. At least some snow. Snow is an entirely different medium than mud and has a tendency to pack and stick to tire tread very unequally, meaning that some types of snow will always fall out of tire tread and other types of snow will immediately pack and turn your tire into a giant snowball, which is not completely realistic to full scale. But regardless, it's something you have to keep track of when you're designing tire tread. So in some snow, these very aggressive tires and the fact that there's so much cross section of tire and so little hang up with the pumpkin meant that Mudv1 was very, very good in the snow to the point that despite the lack of any real use of the center Archimedes screw, I thought there was still some hope in this design. It's worth mentioning at this point that this vehicle, of course, is being built for two reasons. One is a theoretical entry to the Ledgestock Megatruck competition at the time, and it's trying to test out the drivetrain for Decanator. So even if the auger system did not work very well, or even if the tires did not always self-clean in snow very well, I had to keep pushing the design forward because I had yet to test the Decanator's transmission adequately. It had not failed yet, and since it had not failed, I had simply not tested it sufficiently. Because if you ever test something and you want to see what it can handle and how long it will survive, and you don't get it to a state of failure, you've simply not tested it enough. Every design has a failure point, and you will not learn until you've reached it. So this design had to be revised. And what I came up with was Mudv1.1. And we're showing that here now. This is a heavy redesign of Mudv1. It no longer has any sort of auger system whatsoever. In fact, you could argue that in some ways it's such a departure from the Decanator style gearbox. I wasn't going to learn everything I could have because I'm not running a large gear set all the way to the bottom of a drive shaft. But what I was more interested in now was on the survivability of the motor and the motor's gearbox that it was hooked up to. And the reason for this is through testing, I did get a motor failure and I was getting excessive wear in the gearbox. And I wanted to see if this was going to be a problem continuously into the future. So it keeps the motor and gearbox, the metal gearbox attached to the motor, as Decanator would run. Plus, it was going to be running 3D printed gears and 3D printed gears that are mounted in similar manners to the motor. Now, I'm ignoring and not going to cover all the failure modes of how previous gearboxes did not function because, again, this video is already going to be very long. And I'm trying to explain Mudv1 and not how the gearbox works. Yet, this should give me enough information in testing in the new configuration. And in this configuration, I was much more confident that the vehicle would be far better in both snow and mud, as it wouldn't have the auger gearbox system to hang up on or to tip over on. Also, these tires, I already knew were going to be successful because they are a smaller, scaled down derivative of a design that I had tested previously as showcased here. These wheels were actually made for my Savage for hill climbing. They were never mounted to the Savage, but instead mounted to an early version of Mega Portal, the Mega Blackfoot. And I was astonished by how good they worked in the snow. They were probably the best snow tread I'd ever seen. One of the reasons was that snow cleared out of them very well and didn't stick to the tread design. So I simply scaled down the tires and put them on Mudv1. Now, Mudv1 in this configuration was massively more successful. It had none of the issues the previous version had with getting hung up or tipping over because of the low-hanging gearbox. And the tires of this tread design really shined in snow and mud and provided excellent traction, probably some of the most traction I've ever seen with an RC car. With the very small hang up between the tires, this vehicle had the ability to saw through snow and mud and earth until it finally got enough traction that it would go forward. It was a very impressive feat. At the time, Mudv1 was probably the best mud RC we had. However, because this is a test bed and it's using unproven technology and I'm pushing it to the point of failure, since that's the whole point of why it exists, I did start noticing some issues. One of the big issues I was having was now that I could actually run Mudv1 for very long periods of time in extremely difficult terrain that would put the motor under load, I was getting too much heat buildup in the motor. So the heat would transfer from the motor into its steel like transmission housing and then into the plastic parts of the transmission. And it would start melting the transmission housings to the point that the motor would sag and the gears would separate and it would not function. Now, this was a huge issue because the Decanator gearbox, while slightly different in design, was exactly the same in how it was mounted. This would drive me to consider many possible solutions, one of which is, of course, 3D printing in a higher temperature plastic. However, due to the limitations of what I will allow to print in my house, I do not want noxious fumes being printed in my house, so I only use PLA. And ABS isn't really that much higher of melting temperature. Polycarbonate would have been ideal, but again, my health and the safety of those that live in my house are not worth printing in any other material. So I was going to have to use a 3D printed PLA transmission slash gearbox. The solution to fixing the melting issue was to remove a section in the CAD model and cast a solid block of JB Weld into that space and then use a 3D printed jig to line up where the holes needed to be, and then I would bore through the JB Weld plate and mount the motor to the JB Weld. It seems like a really roundabout way of doing it, but it was actually very easy to make, as you just print out the part, place it on the ground, pour in some JB Weld, and then just wait for it to cure, and then drill out 5 holes, and mount it up. And the test was a complete success. It had to be a success because this was going to be the gearbox I was going to run at Shred the Ledge, another huge RC off-roading get-together where it's more like an endurance run where you're allowed to pretty much run anything with straight axles through a very, very long, muddy, rocky, rooty gauntlet of off-road terrain. And I was going to take Mudv1 to this. Mudv1 ran flawlessly, with quotations, asterisk there, for over 6 hours, and it was obvious that the overheating issue was completely alleviated. I would not have to worry about Decanator's gearboxes melting as long as I did the same trick to them. However, a new problem arose. At this event, there was mud. Of course, there was mud. This event was pretty much based around being in muddy, watery terrain, and Mudv1 isn't called Mudv1 because it was designed for other materials. It's designed to go through mud and had been driven through lots of mud. However, this event had very, very, very sticky, gooey mud, and I had not had the opportunity to drive Mudv1 through this kind of mud before. I had driven through lots of watery, thinner mud. And at this point, it's worth noting that we had not found the trench or the super slog mud holes yet. I had thought it was a good mud machine. It had always been good in mud. It floated and it pulled itself and paddled well. But this mud proved too much. This is a huge issue because the motor mounted to this gearbox is a very powerful 550 series motor. It's 3 times the wattage of a lot of the other RCs you'll see on this channel. And if this didn't have enough power to move the tires in this kind of mud, this motor combination would also not have enough power to move Decanator. Now, it's not a simple matter of gearing down the drivetrain because this RC is already very geared down. It is just walking pace. This RC is as fast as a factory stock Red Cat Everest 10. And if you've ever seen one of those, you would know that it's very, very slow. So there was no way I could gear down the solution more than I already had. Now, the issue wasn't entirely unknown to me. I'd seen the motor bog down in other situations, but never to the point of stalling out entirely. And this, I eventually came to the conclusion, it's a wordy way of saying, there was too much resistance in the transmission. Now, this being the second version of the transmission, actually has less gears than Decanator. However, the majority of the resistance is in the transmission that comes with the motor. This Chinese 550 series brushed motor has a very convoluted little gearbox attached to it. It's what fits in that cylinder. And I had broken this gearbox before in testing. And upon inspection inside, you'll quickly realize there's no bearings, no bushings. It's just a whole bunch of little steel and brass machined gears on shafts that just rest in pockets, rotating. And under lots of load, excessive load, the binding of all those little shafts, I'm pretty sure is the vast majority of what keeps power from flowing through the drivetrain. So pretty much the drivetrain was very inefficient in Mudv 1.1 and 1 it would have been as well. And this was an issue that needed to be overcome. At this point, we're now about 2 years into the development of Decanator's gearboxes. It's had over 12 iterations, multiple variations of those iterations, and almost every single problem that the gearboxes had have been worked out, except I've now found that the primary issue is the motor itself, which is a big deal because the motor is the primary gearing down mechanism. The gearbox is more of like a gear transfer power system or like a torque transfer box than a transmission because it doesn't do too much gearing of its own. So if this motor combo would not work, Decanator itself was almost dead in the water, as I would have to completely revamp the gearboxes. Also at this point, we had built many different types of mudding and off-roading RCs, and problems with Decanator's design were becoming apparent without even building Decanator. Center of gravity is something that you really can't underestimate, and Mudv1 had proven that its tire track, its width to center of gravity, was very poor. And even by installing lead weights in all of the tires, 2 ounces per tire, yes, that's like that's a half a pound of lead below the axle line. It would still tend to tip over, and Decanator would have much more weight above the axle line, as it would have 5 motors. This only has 1 motor. It would have multiple batteries, multiple ESCs, and it wouldn't actually be any lighter because the tires are tucked in so tight. Decanator was becoming less and less attractive to build as its inherent downsides were becoming more apparent to me. Just as the Archimedes screw design did not work, Decanator's design was also not going to work for a couple of other reasons. At this point, I had figured out all the technology limitations, all the printing techniques, and all the shortcomings that I'd have to hurdle over to make Decanator work. And I didn't really see it being that big of a step up over the other RCs we had constructed. Vehicles like the Mega Blackfoot Mega Portal would just be so much better than Decanator in almost any given situation. That Decanator's extreme complexity wasn't warranted. This put Mudv1 in a sort of limbo state. What was Mudv1 even for anymore? If it's not for prototyping Decanator components, and it's not for the ledge stock Megatruck competition. At this point, the way that the rules had changed, the tires would not have been legal. Also, we had simply built way better mud trucks that just put this truck to shame, just because they were more unlimited and less based on being kind of funny and sleeper with smaller tires. So Mudv1 sort of was at an impasse. There were elements working with Mudv1, and I could see a much more efficient vehicle that could utilize what I'd learned about Mudv1, but optimized to its fullest, and that would be Mudv2. Mudv2 was not a departure from Mudv1's architect. It was simply minimized, simplified, and made into as compact a package as possible, as the goal of Mudv2 was, well, being a mud Humvee, but this time not a Hummer H2, a Humvee H1. I found this very cool hard body ABS plastic RC, and I wanted to completely conceal within its confines a super capable, quote unquote, scale looking mud truck. One that would, like Mudv1, perform way better in the mud than you would assume by simply looking at it. This truck is better in a lot of ways than Mudv1. It has the same suspension or lack of suspension geometry with the axle housings. It has offset servos above the waterline, the motors above the waterline. Everything is similar to Mudv1, except in a more compact package and using less unknown components, meaning I went back and ended up using a Gen 7 Red Cat transmission for this with a custom water jet cut 7075 aluminum motor mount adapter that I designed and had fabricated. This actually holds a Mini Summit's brushless 380 motor, which you would think would be really underwhelming. However, this design is extraordinarily geared down, and it's only running 2 cells. So what you end up with is a mud truck that's very lightweight, has better center of gravity because you have a smaller, lighter motor up high, and has an unlimited duty cycle. You can just pin the throttle in this thing in a mud hole, and as the videos have demonstrated, it is completely unstoppable. It will eventually make it to the other side. It'll do that because it has less hang up, than has tires pulling forward. It also has a smaller belly that's located higher up, and the tires provide flotation, unlike in Mudv1, so that all the weight of the body and the undercarriage isn't resting on mud. That allows it to just keep pulling itself forward. Despite having significantly smaller tires and less kind of everything going on for it, like less aggressive tires than Mudv1. Mudv2 is very likely the better mud machine. And I say very likely because I have yet to bring both of them to the same mud hole where one machine outperforms the other. It's just kind of funny that way. Despite the fact that you will have now seen Mudv2 make it through the trench very slowly, but all the way. At the exact same day, I had brought a new version of Mudv1 with me, Mudv 1.3, which was now also using a Red Cat transmission, made more light, and just had other modifications to make it better gearing. It was no longer running a 550 motor. It was running a 540 35-turn motor, which sounds like it'd be weaker, but because the transmission was much more efficient, it doesn't bog out anymore. anymore. It just keeps turning the tires. And as this video demonstrates, Mudv1 in its current configuration can complete the trench faster and easier than Mudv2, but they both complete the trench. So neither has an upper hand yet. The only hole that one RC beat the other was the frog hole. Mudv2 makes it through the frog hole. Mudv1 failed to do so, but because of mechanical breakage. And in this video, you hear that horrible noise. I was worried that my custom axle holding mount, whatever you want to call it, I thought they were too tight and they were clamping the gears into too much of a mesh. So I loosened them, but I loosened them too much and it allowed the gears to cog past each other. It was strictly something that I messed up. It was an experiment. It was something that it's the same technology that B50 is running, and I wanted to test loosening them on Mudv1 because, again, Mudv1 is a test bed and I would rather break it than B50, which I know works. And it broke. So they didn't actually get an equal run through the same mud hole. And in the super slog, neither managed to complete that hole. Though, given enough time, Mudv2 might have been able to. There's just not enough battery life left in the camera, and Mudv2 had just completed the trench, so it was very tired battery-wise. So we'll have to revisit the super slog with both machines when they've been upgraded again. So I think that brings us up to the present. That was very long-winded. It was more of an essay on off-roading in general than just what Mudv1 is. But in essence, Mudv1 is off-roading distilled into a test bed of technology that I can try out. And in no way is Mudv1 off the table yet. We now, in the moment of filming this, Mudv1 is torn apart without its axles because the pinions and the ring gears need to be replaced after utterly destroying them, or at least really messing them up in that mud hole and driving it all the way back to the car, 1 mile down a dirt trail in that condition, as you saw in the video. But those axles may not be going on. I have a new axle design, which has been built from the ground up. It doesn't use any Red Cat components whatsoever, and it is the future axle of an RC as of the making of this video. It has not been completed, called Bogger Max. Bogger Max is an evolution of B50, and it will be hopefully better in every way. But the axles haven't been proven yet, and I may run the axles in Mudv1, being just yet again continuing its lineage of testing new technology. Even if that new technology means you'll often see Mudv1 failing, where the other RCs do not, because the technology that ends up in Megaportal, in Mudagon, in all these other RCs trickled down through Mudv1 first.